Hey everybody, I'm Brad. I'm the co-founder of Roboflow. And this week I've been diving into YOLO11. So I've got a whole bunch of results to share with you and some fun integrations. So I'll kick things off here. Um, First off, a brief overview of what we're going to cover in today's webinar. So first off, we're going to talk about the YOLO series and the history leading up to this current release. Then we'll talk a little bit about the performance of YOLO11. I've benchmarked it across a wide variety of data sets already, and I'm excited to share the performance with you guys, and we'll even have a little bit of audience participation there. Then we'll talk about how you can use YOLO11 inside of Roboflow. We've got a whole bunch of integrations across the whole product suite. So excited to get those in your hands. Many of those launched yesterday afternoon or this morning for the first time. So a lot of that should be new information for basically everybody. Then we'll dive into a live demo of YOLO11. I've prepared some workflows where we can test it out, and I'll drop you all a link where you can try it out as well. And we'll talk a bit about the licensing and how you can use YOLO11 inside of your commercial projects, and then we'll open it up to Q&A. If you are on YouTube, the Q&A probably won't be on this video, so definitely check out roboflow.com/webinar so you can join these live and participate in that for future ones. We do these every Tuesday. So to kick things off, YOLO is coming up on its 10th anniversary soon, which is really exciting. I know my co-founder and I have been intricately involved since about the YOLO v4 days. I think we were up late one night and saw that drop on GitHub, and we're amongst the first to break the news of that and to put it through its paces. And then we've been involved in every YOLO since then. There's kind of two lineages that have taken place. The one is the original from Joseph Redman, that was launched under a machine learning library that he created called Darknet. And that one kind of followed its way all the way through YOLO v2, through the exit of Joseph Redman from the computer vision community. Apple acquired the company that he created, and Darknet kind of followed its way through. But in the meantime, PyTorch has gotten really popular. And at the YOLO v5, or even a little bit sooner, there was a fork at the YOLO v3 level. There was a PyTorch implementation. And so a lot of the later versions of YOLO have been implemented as PyTorch, and Ultralytics has been the one that spearheaded that. But then there's been a bunch of offshoots from others like Meituan, and even the original team that took over Darknet is now working on the PyTorch branch. So these have produced market improvement over the years. It's kind of crazy how an architecture that is almost 10 years old is still pretty state-of-the-art if you're looking for a fast real-time detector that's pretty accurate. And the cool thing is that these are super fine-tunable as well. So for YOLO v11, this was released last week by Ultralytics. It's their successor to YOLO v8, which was their last release. It loops in a lot of the learnings that we've had from YOLO v9 and YOLO v10, and some of the others from the community to put those into the mainline branch and come out with a new model that they claim is a bit better. This is their chart of kind of how YOLO v11 fares compared to other YOLO models. The way to read this chart is that going to the left means it's faster and going up means it's more accurate. And so things in the top left corner are the best. So this is supposed to be a better trade-off against these other models where it's both faster and more accurate. Notably, this is tested on the COCO dataset, which is something that Microsoft released a number of years ago of common objects in context. So this is things like toothbrushes and people and bicycles. And so I was actually curious how this would do when you fine tune, which is most of what our users are doing in Roboflow. They're taking these COCO base weights and then training them to detect things like defects or sushi rolls or any number of long tail objects. So again, these are the claimed improvements on COCO. So there's about a 1.4% improvement on the MAP and a small improvement in speed. I actually tried to benchmark this and wasn't able to replicate this just yet. But probably there's some settings that I can do to get things faster with TensorRT and all that. So we'll do a follow-up later with speed benchmarking. But for now, I think the main thing is this improvement in MAP. It's also slightly less parameters, so the download size is a little bit smaller. But in practice, that's probably fairly negligible. But the most time that I've spent this week is putting this through its paces on the Roboflow 100 dataset. So the Roboflow 100 dataset is something that we created as a new benchmark to compete with COCO, where COCO is really trying to evaluate how things do on common objects. We wanted to create something to evaluate how a model will do in the real world against real life data sets. So at Roboflow, we've had hundreds of thousands of users create hundreds of thousands of data sets across a wide variety of domains. And many of those are shared as open source on Roboflow Universe. So the Roboflow 100 dataset, we went out and we sought out a diverse set of 100 different data sets to use as a fine-tuning benchmark. And we've put many models through their paces across the years on this benchmark to see how they fare and to see what's best for use in the real world. This has data sets for everything from handwritten digits to cancer cells to underwater things to video games, kind of you name it, aerial imagery, infrared. Most of the domains that you'll tackle are in here. So this provides a great benchmark against how a model would do once it hits the real world. And notably, many of these data sets have labeling errors or weird ontologies that match what users actually create in the real world. So that helps understand how generalizable a model is. We presented this at CVPR in 2023 alongside Microsoft and did a workshop and a contest. It's also become pretty useful for benchmarking zero-shot models that are used via tuning, but today we'll focus on the fine-tuning aspects. So thanks to our friends at NVIDIA for sponsoring a 8X H100 machine for us to test on this week. I have trained YOLO11 hundreds of times now across these 100 data sets. I think it's probably bordering on 1,000 fine-tuning runs. And so here are some of the results of these training runs. I'd love to get some audience participation here. So I've got 3 models up here, and I'm curious if you can guess both which one is which model and which one you would use in real life situations if you're given these benchmarks and wanted to pick the best model. So if you're on YouTube, leave your guess in the comments. If you're here with me in the webinar, drop your thoughts in the chat. Before I lift the curtain and reveal which model is which, I'd really love to get you guys on the record for what you think is the best model here and which one you think is which. Anybody willing to put their guesses into the chat for Model A, Model B, and Model C? While you're thinking about that, I'll explain how to read these charts. So we took the baseline of YOLO V8 that we had trained about a year and a half ago, and then trained these other models and compared the MAP, so the mean average precision of how accurate they were against that baseline. Something that is much better means that the MAP improved by more than 10%. Something that's better means it improved by between 1 and 10%. We counted a tie as something that was within 1% MAP, and worse was the exact opposite of better, a less than 10% reduction, and much worse is greater than 10% reduction. So I'm looking at the chat here. It looks like one person thinks A is best. A bunch of people going with option B here, getting 2 that are much better and none that are much worse. We've got a stack ranking here of best for Model A and the ranking of A, B, C. So again, put your comment in the comments on YouTube. I would love to get your unbiased opinion before I lift the curtain. I'll give like 3 more seconds. All right, and the winner is none of these because these are actually all YOLO V8. So this shows that across various training runs, there's actually a lot of difference based on the random seed that gets chosen and just kind of luck of the draw. So in order to eliminate this need or this variance, you actually want to train these models multiple times and then either take the best or the average of the results because just rerunning the exact same thing can give you different results the next time around. So I've seen already some people claiming that one model is better than the other on LinkedIn this week, but they've only run it one time against one data set, and it's just really impossible to tell based on data like that. So what I did was I went ahead and ran each of these models, YOLO V8, YOLO V9, and YOLO V10 3 times. I took the best result because it looks like there's some outliers to the downside that are 30 to 40% MAP worse. It's because of either luck of the draw or potentially a bug in the training routine. And I wanted to get rid of that noise and see how the models actually fared against each other. And so these are the actual results. So I'll let that sink in for a little bit. Interestingly, nothing improved on average by more than 10%. We had a couple that were much worse. Interestingly, YOLO V10 seems to be kind of worse across the board, even though our benchmarks on the COCO dataset show it being slightly better in terms of accuracy. If you go to leaderboard.roboflow.com, I think YOLO V10X is the current champion on COCO. But when you look at it across all the datasets on Roboflow 100, it seems like some of the trade-offs that they made to improve the performance on Cocoa degraded the performance when you fine-tune it for some of these long-tail domains. But when you compare YOLO v9, YOLO v8, and YOLO v11, they're all fairly similar. There's some data sets that do better and some that do worse, but most of the time they're within one MP of each other. I'd love to do some more work here. These are preliminary results, but I'd love to dive in and see if there are certain ones that it does better on. I know anecdotally folks have said that YOLO v9 does better on small objects, but I haven't had a chance to dig in on whether that's true and whether these 26 data sets that YOLO v9 did better on and these 24 that YOLO v11 did better on are the same data sets, or if they are stronger at different things. That'll be interesting follow-up work to do. I guess my recommendation for everybody here watching this is, number one, maybe just try them all. I know that's what we kind of do anyway, but if it's specific to your problem, you can test them out. They're fairly interchangeable in terms of how you use them, and I'll show that here in a minute. But what works on your data set might not be the thing that is best on Cocoa and might not be the best on somebody else's data set also. And then the big thing is, like, your data matters so much more than your model. I can almost guarantee that just changing the class list to be more accurate, labeling more edge cases, being more consistent with these labels is going to have way more of an impact than switching from YOLO v8 to YOLO v9 to YOLO v11. And so I would definitely focus a lot of time and effort on making sure that the data that you're feeding into the model is matching what you're seeing in the real world, and that the predictions that you're expecting out of it are what you actually want to use in production. That's going to be much higher leverage use of your time, especially for data sets like most of our customers have that are hundreds or thousands of images versus hundreds of thousands or millions of images. There's just not that much to learn in a typical 200 image data set where the model is the bottleneck most of the time. It's almost always the data. So going forward, I know that I think most of you will probably not just take my word for it that all these models are fairly similar and are going to want to try things out yourself. And to be fair, that's also what I did over this last week. So at Roboflow, we want to make that super easy for everybody. So for the last week, we've been integrating YOLO11 across all the pieces of the product. Starting off with the custom training notebook that we launched on launch day. If you go to roboflow.com/notebooks, you can get access to this training notebook. We have a data format that exports so that you can train super easily any data sets that you have in Roboflow or any data sets from Roboflow Universe, and fine-tune, change up the settings, the augmentations, all that sort of stuff, and see what the best score you can get on your data set is. We also built this into Roboflow Train as a one-click training integration. So if you just want to use most of the default settings, just choose the model size. You can now just click Train in Roboflow and compare, baseline and see if it's way better or way worse, or if it's close, and whether this is worth investing more time in. This is something that we hope to do a lot more. We've built out the infrastructure now to easily add more of these models. So over the coming weeks, you'll be seeing more architectures and more task types being supported inside of the platform for training on our hosted GPUs. We also added this to our serverless API. So any model that you train in the notebook or in Roboflow Train, if you load it back into the platform, we'll automatically deploy that to a serverless platform that scales from 0 up to infinity, and you just get an API endpoint that you can hit. So you don't really need to have beefy GPU machines if you're running at low volume. But we also have options for self-hosted and hosted GPU inference as well. So our open source package inference, which is available at roboflow.com/inference, which should take you to our GitHub page, has full support for this across workflows and our APIs and inference pipeline. We also last night added support inside of Roboflow.js so that you can use YOLO11 in your web browser. I won't do a demo of that today, but we'll probably do a follow-up. And you can, if you're on the YouTube, you can probably go to universe.roboflow.com and search for model:YOLO11 and find a whole bunch of models that you can try out in your web browser that people have fine-tuned and shared. We also have support inside of our iOS SDK so that you can build native apps for Mac or iPhone using your YOLO v8 or YOLO v11 models. We also have support for our auto label tools. So this is great for pre-training when you have a model trained and want to label more data. You can start from the model's predictions versus from scratch. And you can do that both in batch across an entire batch of images or one by one in our label assist tool. And then finally, in our open source ecosystem, I mentioned inference has support already. We also have support for parsing these predictions in supervision and for visualizing them and working with them downstream. And also in AutoDistill, which is our framework that uses giant LLMs to train fast detectors. YOLO11 is already a target that you can train in an automated pipeline. So as you can see, we've been leaning in heavily here and should be the easiest way for you to test this and see if YOLO11 is for you. We'll leave a bunch of these links in the YouTube comments or description section. And then if you're live here with us today, James has been dropping a bunch of these in the chat as well. So with that, we'll hop into a demo. So I have prepared a few workflows in Roboflow here. Workflows is our product that lets you easily mix and match and chain and combine and share computer vision pipelines. So here I've got a workflow that just accepts a model parameter, which we'll use to test the different versions of YOLO11, the different sizes. It runs them through an instance segmentation block and then does some visualizations. So if I go over here, I have saved an output. Right now, we're going to use the nano size of the segmentation model. And if I hit run, I can see that I get a visualization and the model predictions. I'll blow this up so that you can see it. First thing that we notice is it missed a lot of these people. And so up here, some of these small people didn't work that well. One thing that I was curious of was what if we increase the size from the nano size to the extra large size, which is the largest. So I'll go ahead and do that and run this again through YOLO11X 640 and see what we can get here. Should be downloading the weights here, which will take a second for them to load up. And then you can see actually it didn't find those small objects there either. And we'll see in a minute how we can approach solving that. But I'm going to go ahead and share this workflow with you all in the chat, and we'll put something also in the YouTube description so that you can try this out. But if you go to that link that I dropped in the chat, you should get a view very similar to this, be able to just go to test workflow. You can upload your own image if you click the X, just select a file from your computer. So here I'll try this dog one and see what it predicts. It looks like got most of them, but missed 3 of them. We'll test this out again in a second. So the first thing I want to do is show how we can get around that. So going up the size in the models didn't really help on this model to detect those small people. But with workflows, it's super easy to use Sehi. And so this is the exact same workflow. I just added this slicer and stitcher, which will take that input image, split it up into a bunch of smaller images, run inference across all of those, and then put them back together into one output. And so here you can see that even on the nano size, if I do Sehi, it detects all of these different people. And actually, I did this on object detection because I'm running this locally on my Mac without a GPU. So just to speed things up, this is doing probably 15 inferences on this image versus just the one. But it finds all these small people. And so this is a great approach. This works not just for YOLO11, but for any other YOLO style model where small objects are something that you want to detect. So that's one approach that I would definitely try. It seems to be just as useful for YOLO11 as it has been for previous versions of YOLO. And then here I've got a bit more fun workflow. So this is a model comparison workflow. What I did was take a single input image and pass it through YOLO11 and YOLO V8. I visualized the output of both of those alone, but then I created this new model comparison block. This should work for you by the time this is on YouTube, but I submitted a PR just a second ago against Inference to add this workflow block. So if you want to test this locally, you'll have to pull this compare visualization or wait till the next Inference release puts this out there. But this is kind of the power of Roboflow Inference and Roboflow Workflows is that because it's an open source package, anybody can come in here and add new visualizations and new code, new blocks. And so I did that last night when I wanted to communicate the differences between these models. So the first thing I'm going to do here is try that people walking again. And so this is going to run it through both models and then show us the results. And the way to read these results is I have this workflow configured such that Model A is the YOLO11, Model B is YOLO V8, and then I've set the color of A to be green, the color of B to be red. And so when I look at this output, anything that is green is something that YOLO11 found that YOLO V8 did not, and anything red is something that YOLO11 missed, but YOLO8 got. And so you can see that YOLO V11 found some of these people, and YOLO V8 found some of these people. I've tried this a bunch of times, and it seems kind of random to me. I can't really tell why one finds them and others don't. It just seems to be differences between the models. But you can see, so that's the delta. This is the output of YOLO11. This is the output of YOLO V8. So you can see it, in fact, did miss those people up there and did get these people down here. So I'm going to try a couple other images here to show the delta between these models. So I've got that dogs picture again. I'll feed that through here and we'll see what's different. And actually, in this case, with the segmentation model, they both basically got all of these dogs, which is kind of interesting. You can see that there's some areas of this photo that YOLO11 predicted as a dog, which I think is actually part of that dog's leg. So that mask is a little bit better. And there's some areas here that YOLO11 properly did not predict. So YOLO V8 predicted this as part of one of the dogs, but YOLO11 didn't, and it looks to me like that's background. So that's actually a good thing that it kind of cleaned up some of these masks. I'll try a different image here. So here's another one of just some people. You can see that like around the edges, it looks like it's predicting more of the masks of the people. It looks like YOLO V8 down here missed this guy's foot. YOLO11 cleaned that up and properly did not predict this tablet this guy is holding as part of the person. So slightly different results. It looks like the 11 ones are a bit better there. Let's see, this was an interesting one. So here's another one of people. And you can see that neither model found all the people, but the people that did find are different. This was one where if I reduce the confidence, it actually gets a lot better. And they find all the models now are finding these people that are shining through brightly. But YOLO11 is finding more of these. It's kind of weird that 11 still misses this person here and this person here. But it seems like probably if you fine-tuned it a little bit on images like this, it would do better. So yeah, so those are some of my demos. I'll do one more, which is one of the cool things with workflows is that you can deploy in a whole bunch of different ways. And one of those ways is on video. So this uses inference pipeline to grab your webcam, and then you can use the results of it to do things in Python. So I've copy pasted this into a file already, and I will go over here and just hit run.py, and this should open up a window on my webcam and we can try it out in real time. This is running on my Mac again, so no GPU. It'll be a little bit slow, but I'll drag this window over here. So you can see the green areas are going to be things that, again, YOLO V11 predicted that YOLO V8 did not, and the red is areas that YOLO V8 predicted that YOLO V11 did not. So you can see like my chair over here, or I guess the other side, this is mirrored. YOLO V8 was predicting as part of a person, and YOLO V11 actually properly does not predict that as part of me. If I hold up my cell phone, I was noticing that YOLO V11 sometimes was predicting this better, though right now it looks like they're both doing about the same. So I'll share this workflow as well, and you can kind of try the difference between different models, and you can hold up different things and see what they do. I think this screwdriver was another one where the tip of it was doing different things across the different models. But this is just an interesting way to compare two different models against each other. And again, you can go in here and edit the workflow and change which models you're comparing against each other just by going in here, clicking on this, and changing out this YOLO V11S with a larger size or a different one, and you can compare against YOLO V9 or YOLO V10 or any other model like Florence or whatever you want. So yeah, with that, that's kind of the live demo. The last thing I wanted to touch on is the licensing. So YOLO V11 is similar licensing to YOLO V8. It's AGPL, which means that if you are using this in a commercial project, you actually need to open source your code as well under the same license, unless you purchase a commercial license. Roboflow is a relicenser for both YOLO V8 and YOLO V11. We're one of the biggest customers of Ultralytics. and provide that as a service to our customers. So whenever you're using these models on our hosted API and our hosted compute, you have a license included just with the usage-based fees that you pay to Roboflow. And if you're looking to self-host things, so long as you're using inference, which is what I just showed, your starter or enterprise will cover you, and you can operate under a commercial license pursuant to your plan's limits on Roboflow. And if you want to use Roboflow train and then use these weights outside of the Roboflow ecosystem, that is something that we can also do an enterprise license on. And so just contact our sales team and we can do a enterprise agreement if that's something you're interested in. But it's much easier to use this stuff inside of the Roboflow ecosystem and across our tooling. And so that's definitely what we usually recommend. So with that, I will open it up to Q&A.